Hello everyone, welcome back to lecture 3 of a lecture series on an introduction to molecular simulations and statistical mechanics for engineers. So in the last class what we discussed was Newton's equation of motion, work, and how to use those two primary concepts in order to derive things like potential energy, kinetic energy, and the conservation of energy. Today, we're going to take a step away from some more theoretical developments, and we're going to look at how to actually solve Newton's equations of motion numerically. So today's class, lecture 3, is on the numerical integration with the Velocity-Verlet algorithm. Numerical integration with the Velocity-Verlet algorithm. So, in general, the idea of studying the mechanics of a system is we're going to be given a system with some positions. So given particles with positions r, I at some time t naught, and velocities vi at some t naught, we want to answer what are the positions and velocities at any arbitrary time. At any arbitrary time t. So we want to be able to look at the evolution of these particles in time. We usually suppose that t naught is less than t, so that t is advancing forward in time. Now, generally we're going to have a strategy here, so our general strategy is going to be as follows. First, given our initial ri's, so given some ri at t naught and vi at t naught, so initial positions and velocities, we're going to calculate the forces on those particles. So we're going to calculate Fi at our initial time. The second step, we're going to integrate the equation of motion over a time step delta t. Now, a time step is essentially a very short increment of time in which we're performing this integration. Now, in the limit that you look at an infinitesimally small time step, that would be dt. That's sort of in the realm of calculus. But numerically, our time steps are going to be discrete, and they're going to be written as a delta t. And what this is going to give us, after integrating the equations of motion, are updated positions. So we're going to have some ri of t plus delta t, and some updated velocities at vi plus t delta t. Now, of course, once we have these, we can just calculate the new force. So we can calculate the force at t plus delta t. And once we have that, we can go back and we can repeat the process. And we can just continually repeat this process of calculating the positions, the force, the updated positions, and then the new force, and so on and so on and so on. And if we do this over enough time steps, what we're going to see is that we're going to be able to watch our particles. So let's say this is a 2-particle system here at t naught, and this is our 2 at t naught, and they have some initial velocities. We're actually going to be able to watch these guys move around, so from here to here, and from here to here, and then there's a new velocity depending on the forces, and we're going to see another time step like this for as long as we want to run or can run our simulation. And what this is going to give us, I'm drawing it on a whiteboard so it's difficult to picture, but this is essentially going to give us a movie of how these particles are moving around. And we call this movie, so if we were to watch all these in a line, we call this a trajectory. So we can actually watch the trajectory of these particles. So now that we know what quantities we're looking for, these updated position and velocities, let's write out what we think this new quantity should be. And the way we're going to do this is with a Taylor expansion. So if we have some quantity Ri of t, and when we want to know how it's evolved in time by some t plus delta t, remember we can write this as a Taylor expansion in the following way, where we have our updated positions are given by our initial position plus the derivative of our initial position with respect to t, delta t, plus 1 over 2 factorial, second derivative of Ri of t, dt squared, delta t squared, and so on. Now these extra terms we're going to say are of order delta t cubed. And this just means that all the other terms are at their largest or most significant contribution in the delta t cubed scale. So these are our positions. Now, looking at this definition, let's rewrite it in terms of quantities that we've talked about already. So what you can see initially is, okay, well, we know Ri of t, and in fact, this is known in our problem, right, because we have some initial position. What is dr dt? Well, that's just the velocity of the particle at t. So this is just the velocity of I at t, delta t. And this last term, d squared r dt squared, is just the acceleration, which we can write through Newton's equation of motion as the force over the mass. So this is equal to 1 over 2 f of I of t over the mass of I times delta t squared plus our order delta t cubed terms. So there's our positions. Now let's take a look at our velocities. Vi of t plus delta t is going to have the same type of expansion. Of course, now we're just replacing the variable names. So we have Vi of t plus dv I of t dt delta t. And then here, what we're going to do initially is we're going to truncate this at the second order. So we're going to have some plus order delta t squared terms. Rewriting this in terms of quantities we know, Vi of t we know, so we leave it. The derivative of v with respect to t is the acceleration, which using Newton's equation of motion can be written as the force over the mass. So Fi of t over mi delta t plus order delta t squared. So we have two equations here. And if we choose to ignore these terms for now, these order delta t cubed in the position and this order delta t squared in the velocity, and we use these equations here, so this equation for the position and this equation for the velocity, This gives us an algorithm that's named the Euler algorithm. The Euler algorithm. Now, of course, we just go back to our general strategy we talked about before. So if we have a system, we take its initial positions, we take its initial velocities, we compute its initial force, which would go into this term here. We plug in whatever our time step is that we chose into this equation to get our updated positions. And that gives us where the particles are next. Similarly with the velocity, we take our initial velocity, we compute our initial force, we plug in our time step, and we compute our next velocity, and we end up getting that trajectory that we're looking for. Now, there are some issues with the Euler algorithm, and we're not going to go into them in this lecture because it's part of your homework to show this. But one thing about the Euler algorithm that's important to remember and to note is that this algorithm does not conserve energy over a long amount of time. So in your homework, you're actually going to do a little simulation of a simple harmonic oscillator. You're going to find the analytical solution for the harmonic oscillator, and then you're going to implement the Euler algorithm on it. And I'm going to have you try to plot the energy, the total energy of the system, the kinetic plus the potential part, of the analytical solution, which will just be a straight line in time because of the conservation of energy. But what you're going to find with the Euler algorithm is that over your time steps, the total energy is going to go up. And what that means is that the algorithm itself is not conserving energy. So this scheme that we have here is actually not going to be good enough for us to do time integration of Newton's equation of motion. We need to find something that conserves this energy better. Now, how do we do that? Well, we use the Velocity-Verlet algorithm. I'm telling you, and for now you're trusting me, that the Euler algorithm does not conserve energy. And you can prove this yourself by studying some simple systems. But now I'm going to talk about how we can actually amend this problem. And this is going to be the Velocity-Verlet algorithm. The Velocity-Verlet. Now, to develop this, we're actually going, it's actually pretty simple. We're just going to take one little extra step that we didn't take in the Euler algorithm case. So we're going to write our updated positions with the same Taylor expansion. Ri at t plus delta t is the position at its initial time plus its velocity at that initial time times delta t, plus its acceleration, and we had a factor of 1/2 delta t squared. And then of course we have our order delta t cubed terms. So that stays the same, but now we're going to do something a little different. In the velocity term, we're going to extend the order of which we look at this algorithm here. So we're going to take vi of t plus, and we already wrote this out, so I'm just going to skip ahead, fi of t over mi delta t. Now we're going to go one term further, like we did in the position, 1 over 2 factorial. Now we have the second derivative of v. dt squared. And then we're going to cut it off. Delta t cubed. What am I missing? There should be a delta t squared here. Well, we've already written these terms in in terms of variables that we know, but what about this term, the second derivative of the velocity with respect to time? Well, the first derivative of the velocity with respect to time was the acceleration. So the second derivative is actually the time derivative of the acceleration, which was Fi over Mi. So let's evaluate this and think about what this means. Well, the Mi is independent of time, so this is just 1 over Mi, times the derivative of the force. Now, we don't really have an intuitive quantity for what the derivative of the force is, just naturally from our simple classical mechanics we've looked at so far. But one thing we can do is we can make an approximation for what exactly the derivative of the force is. And to do that, we're just going to invoke a first order approximation to this quantity. Now, recall the definition of a derivative. I'll switch colors here. When we define a derivative, so we were looking at something like maybe the derivative of some function with respect to x, we define this as the limit as some dx goes to 0 of f of x plus dx minus f of x over dx. This you should remember from your Calculus 1. Now, of course, this is in the limit that dx goes to 0. In our case, we have discrete delta t's, so we can't get directly to this limit. But what we can do is we can write this approximately as 1 over mi times, we're going to, in this manner, we're going to write like this. We're going to say this is fi of t plus delta t minus fi of t over delta t. So you can see this is the definition of the derivative without this limit, because we're now in a discrete increment in time here. Now, of course, this is an approximation, and we call this a linear approximation. So we're approximating that the derivative of the force is approximately linear over this time step. Well, this is going to allow us to actually rewrite our equation here, and it looks like maybe I don't have space. So I just erased this bottom line so that we could write out the entire term with what we just calculated. So basically, in terms of the new variables that we just discussed, our velocities are now vi of t plus fi of t over mi delta t plus 1/2. This term was fi of t plus delta t minus fi of t over delta t times delta t squared. Now notice this is fi of t over m, and then we have a minus, well, these are going to cancel, right? Then we have a minus, oh, and there's an m here. There's an m here. So we have a plus fi of t over m and a minus 1/2 fi of t over m, and then a plus fi of t plus delta t over m. So let's consolidate all these terms together, and what we're going to end up with is just combining these. Like, this is pretty simple algebra. I'm just running out of space here. But what we're going to end up with is 1 over 2 mi times Fi at t plus delta t plus Fi at t times delta t. So this is going to be our new velocity term, written in terms of a linear approximation in the derivative of the force. These two equations here are the equations you need to implement the Velocity-Verlet algorithm. Now what we're going to do next is actually write out the strategy for how to actually calculate and implement this algorithm in Python. So our implementation, this is kind of like a pseudocode, implementation or pseudocode, is going to be this. The first thing we're going to do is we're going to collect or keep track of our starting positions. So given our initial positions and velocities, we're going to calculate our force. Calculate our current force at time t. Using this force, we're going to update our positions. So we're going to calculate our next positions. Calculate next positions. And recall, we can just do that because we don't need any extra information than we did in the Euler algorithm. We have all the information we need. R of t plus delta t is just your initial positions that are given plus your initial velocity, which is given, times delta t, plus your 1/2 Fi of t over mi delta t squared. So we calculate the next positions. Now in the Euler algorithm, we could just directly calculate the next velocities since these two steps contained all the information we needed. But in the Velocity-Verlet algorithm, there's a tricky term in that equation, namely the Fi of t plus delta t. How do we calculate the force before we calculate the velocities? Well, technically, calculating the force in these cases does not depend on the velocity. The force is going to come from some potential energy field, which we can calculate only based on the positions. So in a Velocity-Verlet algorithm, what we're going to do is we're going to calculate this. So we're going to calculate the new force. Calculate new force, which is this guy, using the new positions, using the updated Ri of t plus delta t. So we didn't have to do this before with the Euler algorithm. We could just go directly and calculate the velocities. But now we actually need this new force term based on the updated positions to then go to our final step, which is to now calculate the velocity. Calculate velocity. And now we have all the pieces to the puzzle because Vi of t plus delta t is just Vi of t plus we wrote this out, plus 1/2 mi in the denominator times Fi at our new force plus Fi our old one. I ran out of room here, so I'm going to put this delta t here. And this is your implementation of the Velocity-Verlet algorithm. Now what you're going to find, unlike the Euler algorithm, is that the Velocity-Verlet actually has really excellent long-term time or energy conservation in time. So what we're going to see, I'll make a little legend here. Use a couple different colors. So we'll have black be our analytical solution. Analytical. We'll have blue be our Euler, and red be our Velocity-Verlet. When we look at this chart of the energy versus time, we're going to see that, of course, in a simple harmonic oscillator in these systems in which there is an analytical solution. So I should have specified this is for a simple harmonic oscillator. What you're going to show me on your homework is that there's some analytical solution to the energy, which is conserved in time. I keep mixing the colors up. This is the analytical solution, is the black line. So there's going to be a constant energy for the analytical solution. You're going to find that in your Euler solution, as we talked about before, that the energy is not conserved well over time. And we're going to find that introducing this additional term into the velocity, into this calculation, and using this type of implementation is actually going to give us extremely good long-term energy conservation. So just the addition of this one extra term in the Taylor expansion is really going to save us. Now, in molecular simulations, Velocity-Verlet is very commonly used as a time integrator, and there are, of course, a number of other implementations that are either equivalent or can give you access to the same information, including things like the Verlet algorithm and the leapfrog algorithm. For the purposes of this class, we're just going to focus on the Velocity-Verlet since practically and conceptually, I think it's the easiest to understand and implement within Python. Well, thank you guys so much for tuning in to this lecture on numerical integration of the equations of motion. And what we're going to get into next time is a bit more of the physics of classical mechanics. And we're going to start to reframe Newton's equation of motion in terms of some maybe less familiar quantities, including the Lagrangian and action. And from this, we're going to be able to derive a new set of differential equations, or a new differential equation called the Lagrange equation of motion that is equivalent to Newton's equation of motion in every way, but can offer us some very unique advantages with respect to the number of coordinates required to study the system. Later, the Lagrangian will be Legendre transformed into a Hamiltonian, which is going to give us the framework to start to understand statistical mechanics and also quantum mechanics as well. Thank you all very much. Have a good day.